This is an example of an AC node solutions problem in Circuit Tutor at level 4, or the mastery level. As always, we do have examples available at multiple levels of difficulty, and it would be a great idea to look at some examples prior to trying to work the problems. So right now I'm going to go straight into a problem. And as always, in nodal analysis, our first task is to select an appropriate reference node. Remember that if you fail to select a reference node, then you would not be able to determine absolute values for any of the voltages involved in the problem. So remember that we usually want to place this attached to as many elements as possible, and preferably to voltage sources. So we could go, for example, here would be 3 elements including a dependent source. Here's just would also be the same. Here would be similar. Here would just be 3. So really, all 4 choices here are roughly equivalent. So I think I'm just, for simplicity, going to go to the negative side of the independent source, but it doesn't matter too much. Okay, so being a solution problem, we have been given the KCL equations already for this circuit, so we do not need to compute those for each node or supernode in the problem. But we do need to compute the voltage constraint equation, which would apply for each of the 2 voltage sources, the independent source and the dependent voltage source. And we'll also need to find the equation for the control variable of that dependent source, which again is a voltage-controlled voltage source. In other words, we need to find an equation for Vx. And finally, we need a SOT variable equation for the SOT variable, which in this case is this current I0, which actually is that of the dependent voltage source, or flowing out of the, coming out of the, rather, of the positive terminal. Okay, so let's go ahead and do that. And we'll do the voltage constraint equations first. So let's do one first for the V1S source, the independent source. And we notice that it has one end connected to ground of the reference node and the other end connected to a non-reference node. So that will require 1 node voltage. We're not allowed to enter, for example, V0 here, so we'd have to just use 1 voltage. And that will be equal then to a fixed value of the independent source. And since the positive side is connected to V4, that will just be V4 with a plus sign. Now, if it had been the negative side connected to V4, then it would have been negative V4, would have been equal to this value, which is, I'm just going to put the value of the source. So V1S, we get that down here, that's 8 angle 0 degrees. And we'll check that equation. And that is correct. Now the second voltage constraint equation needs to be written for the dependent or controlled voltage source, which is a voltage controlled source. So again, we notice that it actually has the voltage on both sides of that are both node voltages. They're not reference nodes. So therefore we need a difference of node voltages, and that will be equal. Now instead of a fixed value, we need to use basically the value is written on the diagram, which would be a voltage controlled voltage source. And notice the tooltip there shows us that that would be this term here, which obviously has the correct form. Remember, the alpha stands for any alphabetical character, like an X, for example, and the number sign indicates you're going to put a number there. Okay, so we're going to notice that the positive side here is V3, the negative side is connected to V2, so therefore that should be positive V3 minus negative, well, minus V2 rather, and that will equal the value of the source, which is just that 2Vx. So again, we're always paying attention to the polarity, so that we have V3 minus V2 and not say V2 minus V3 and not putting a minus sign here. Okay, so we'll check that. And that is correct for the second voltage constraint equation. And we've done enough of that, so now let's do the control variable equation for the dependent source. And remember, the control variable is the value of Vx. 2Vx is the output voltage of this, which is double the input voltage, which is the Vx, the value across this inductor. So select control variable equation, and then we're writing an equation for Vx, so we need that term. Remember, the alpha will be replaced by x here, and that's simply going to be a difference of node voltages, except in this case, one of the nodes is the reference node, so basically that will be 0, and so we just need a single node voltage to express that. We couldn't use this term, for example. So we fill in the x there. And we notice that basically the positive side is connected to V2. So that'll be equal to plus V2. It's really V2 minus 0, but that's the same thing as just plus V2. So that should be a very simple equation. Basically, Vx is identical here to V2. And that is correct. And then our sought variable equation will be for the current flowing out of a dependent source. So and that's a single branch, so we call that a branch current. And of course we have I naught equal to. And now we have to think about this because the current out of a voltage source, well, that's whatever it needs to be. Remember, that's not actually determined directly by the voltage source's value. Instead, it depends also on the rest of the circuit. And so it's whatever it needs to be. So how will we determine what that is? Well, remember that in nodal analysis, the answer to almost any question is KCL, because nodal analysis is based on Kirchhoff's current law. It's a systematic application of KCL, hence that's why we write KCL equations, for example. So in this case, to find a current, you can bet that we're going to want to use KCL. So clearly we could apply it, for example, to this node here, and the current flowing into that node would be I naught, and then we could make that equal to the currents exiting that node through these other two branches, which we can then compute from node voltages and from the value of this current source. Now we could equally well do it on the other side of the source by summing the current that's going this way through the inductor and this way through the resistor, because those currents then join basically to form the current I naught. So we have two choices of how we could write that equation. It doesn't matter too much which way we do it. It may be a little bit simpler in this case on this side, since one of them is just a value of a current source. So let's do it over here. Circuit Tutor will accept either of those valid equations. So first we need a term for a current source value, which will just be a fixed current, as indicated here. And again, that's constant current source, fixed value, as the tooltip says. Or down here, you could, well, if you're pointing at it, down here you can read it. And then through the 8 ohm, we need a difference of node voltages because neither end is connected to ground. So we need a term like that, which will add, and those two currents then will sum to I naught. So first we need I naught is going to go partly this way and partly this way. And so this will actually be opposite to the direction of I naught. So we need to subtract the value of that current source because this arrow implies going this way, which is the negative of the reference arrow direction for the current source. So the I1S then is 8 angle 80 degrees. So we fill that in. But again, very important to have the correct sign there, and that's going to be negative in this case. And now again, we want the current going this way through the 8 ohm source. So we would take, using Ohm's law with a positive sign, we would take V3 minus V4 divided by 8 ohms. And in a sense, we can use the analogy that water always runs downhill. The resistor being sort of like a trough or something that water would run through. And so it always goes from the high voltage, if you like, V3 to the low voltage V4, if you want to think of it that way, even though they may not really be, V3 may not be greater than V4, but we just assume that for the purposes of this. Okay, so that's our equation, and now we'll check that. That's probably the trickiest part of the problem, is remembering that, again, if the question is about nodal analysis, the answer is nearly always KCL. Okay, so now we have nearly all of the equations that we need for this circuit. So we'll just click No More Equations. And now, because this is a solution tutorial, we have to prepare to actually solve these equations so that we can compute the desired sought variable I naught. Now, to do that, we want to first put them into standardized form, which basically involves simplifying these equations and putting all the constants on the right-hand side. Now, remember that as we do that, we can, if we wish, multiply equations through by a constant, say if we wanted to clear the fractions. So, for example, you might want to multiply this by 72 if you wish, the product from 9 and 8, to clear those fractions, although it wouldn't clear the negative j, but that could just become a plus j in the numerator, so that would actually take care of it. And here, well, the common denominator there would be, again, 72, because 3 is a factor of 9, so that would be sufficient if you want to do that. but we don't need to do that, and I'm just going to skip that. And you cannot, however, combine equations, or for example, substitute this into here, or substitute these into wherever. You cannot make substitutions. That will not be accepted. So instead, we're just going to basically transcribe the equations, maybe multiplying them by a constant. That's explained here. Okay, so we have the form, and remember that we're not going to enter the SOT variable equation down here. That will be used later. So the first equation, and notice we have 1, 2, 3, 4, 5 equations, and then 5 rows on our form. So that matches up. Okay, so the first equation is just v3 minus v2 is 2vx. So we'll bring the 2vx over to the left-hand side by subtracting. So we have 1v3, and then we have a negative 1v2, since we're subtracting v2. And then we're also subtracting 2vx, so we'll have, for a coefficient of vx, and notice that's one of our unknowns here, in addition to the 4 node voltages, we have a fifth variable here, which is the control variable for the dependent source. Although that really is, in this case, equal to one of the node voltages, but we haven't used that fact in writing these equations. So that would be negative 2. And then the right-hand side will be 0 because there's no constant term in that equation. Then the next equation would just say v4 is equal to 8 angle 0. So v4 will have a coefficient, of course, of 1. All the other coefficients would be 0. And then we just put the 8 angle 0 over here. The third equation is a KCL equation. And we would see that we have v1 has a coefficient of 1/9. And then and that's going to be the real part because there's no j's there. And then it also has a complex part involving a j. So the 1/9 we can enter easily. That's because we know that 1/9 usually is going to be just 0.1111. Remember, that's a repeating decimal for any number of ninths, like 3/9 is 0.3333 and so forth. Okay, and then for the imaginary part, remember that 1 over j is equivalent to negative j, because j squared, by definition, is negative 1. So therefore, the reciprocal of j is always just negative j. And remember that we also have to take the reciprocal of the 3, because both the j and the 3 are in the denominator. Sometimes people just want to bring the 3 upstairs, but of course that doesn't work because it's in the denominator, not the numerator. So this would be minus j, 0.33. And I'll enter that to 4 digits, so it's a repeating, of course, decimal there for 3 1/3. So that was the, oh, I'm sorry, that's the v, oh, I'm looking at the wrong equation. I'm sorry. So that was the v1. Oh, I'm sorry, I went to the wrong equation. So I had this part, that was 1/8. So that should have been, and that should have been plus j there. I apologize. So let's back up. That should have been plus 0.125j, or j125, doesn't matter. So I'm sorry, I got mixed up looking at the wrong equation. So it's the, again, 1 over minus j is j, just as 1 over j is negative j. So, but again, that's the imaginary part. So it would be plus j1 point, or 0.25 or 125 for 1/8. Okay, and then the v2 is minus 1/9, so that would be negative 0.1111. And that should be it for that equation. And then the next equation, that has, for v1, just a negative 1/9, so that would be negative 0.1111. And for v2 now, we have 1/9 is the real part, and then this part's going to be imaginary, so that would be 0.1111 again. And then the imaginary part would be negative j, 0.3333, as I misspoke before for the other one. So minus, well, j, 0.3333. Remember, the order there doesn't matter because multiplication, of course, is commutative, so it doesn't matter which we put up front. I guess it's actually, when it rewrites it here automatically, it's putting the j in front, but it doesn't matter which way the j is. Okay, then we have for the v3, that's going to be just 1/8 or 0.125. Oops, 5. And for v4, that's going to be just the negative 1/8. 0.125. And finally, there's no Vx here, so we just add the constant to both sides, and that'll be 8 angle 80 on the right-hand side. And as I said, the coefficient of Vx is going to be 0 because there's no Vx there. Okay, and I made a mistake here. I started writing in the wrong row, so what I'm going to have to do is to copy all those things down. I apologize for the confusion there, but that should have been the fourth equation, not the third one. And the third equation, that should have been 0. Let's see, so that would be the 8, and then the minus 1/8, that should have been in the fourth equation. And then this should have been down here, and this should have been, that was the, this one. Should have gone down here, and this should have gone down here. So just a slight mix-up. Actually, it doesn't matter. You know, I could have actually just changed the order of the equations. It would have been easier, I guess, than to move this, but I'll just do it this way. And in this case, this would have been this, again, well, let's, instead of moving that, have the V2, let's just move this equation, it'll be easier. So I'll just take that and move that down here, and move that down here, and just make that 0, and that 0, and that 0. 0, 0. Okay, so I just switched the order of the second and third equations there, which doesn't really matter. Okay, and finally the last equation is simple. Vx equals V2, so we could just write that various ways. Let's put it -1 V2 plus Vx plus 1 Vx is equal to 0. So that should be the full set of equations. And it looks like I messed up on the fourth one here, so let me double check that. So that is -1/9, and this should have been 1/9, which it is, minus j 1/3. Oh, that's what happened, is I forgot the 8 down here. So I forgot the 8 in the 8 angle 80. Okay, so try that again, and that is now correct. Okay, so that sort of reiterates we don't have to do them in the same order. It's probably good to do them in the same order they're written here, but it doesn't matter if they're mixed around. Okay, so now the next job is to cast these in the form of a matrix equation, and we can just press the copy button there rather than retyping all those coefficients. And again, you know, these correspond, each simplified equation corresponds to one row of the matrix equation. So for example, we'd have V1, or this coefficient rather, times V1, this times V2, this times V3, this times V4, this times Vx. So actually the coefficients are written across the top here just for easy reference too in interpreting the equations. And similarly for all the other equations. So we'll check that, and that is correct. And now all of that has been printed on the screen for us. And now we're going to proceed to solve these equations. So now that might look like it's fairly intimidating since we have a 5x5 matrix. I don't really recommend that you do that as a matrix equation because it isn't really necessary here. Notice that all the equations other than the KCL equations are really quite simple. So these are just very simple equations, especially these two, that can be substituted into the other two, and that'll just give us a 2x2 system of equations, which can be solved by elementary algebra. So I wouldn't say that full-fledged Gaussian elimination, for example, while it can be done here, it isn't really necessary. So what I'm going to do then is just to use elementary algebra after substituting, and I'll do that on paper. Okay, and your instructor may ask you to turn in your handwritten algebra. If they do, then you should retain that for them. If not, you may want to keep it just for yourself as a record that you can use when you're studying and trying to remember how to do the complex algebra. Okay, so now we have to compute those values. So let's go on to paper now. And what I've done is simply copy the two, let me scroll over here actually so I can see them better. Copy the two KCL equations, which now, because of the way I arranged them, it's actually the second row and the fourth row. And so this one I've copied up here. So the 0.111 plus j.125, etc., minus 0.11 v2 is equal to 0. So that's this equation. And then the next one down here is the minus 0.111 here times v1 plus this coefficient times v2 plus 0.125 minus 0.125 v4. That's equal to 8 angle 80. So that's just copied over here. And then I also wrote out the constraint and the control variable equation. So v3 minus v2 is 2vx. Vx we said is just equal to v2. And v4 is equal to 8. Don't really need the angle 0 there if we put it in rectangular form. And so we want to solve this now so we can eliminate one of the other variables. Obviously, we want to eliminate vx usually. So we'll just replace vx, but it actually doesn't even occur here. But it does appear here, and so we'll basically put a v2 into here and make that v3 minus v2 is 2v2 over here. The bars just indicate that those are complex numbers. And then we can simplify that by adding, well, actually we could just probably add v2 to both sides and then solve for v2, for example, by dividing by 3. So v2 would then be v3 bar divided by 3, just using simple algebra. Okay, so now let's substitute those results. And notice that now these equations have the vx, so we'll just basically eliminate the v3 bar here and the v4 bar by substituting in. So let's start with this equation on top here. We'll just write that down here. So we have the original term for v1 bar, and then the v2 bar, remember, is v3 over 3. So I just divide this coefficient by 3, which I can do on my calculator. And it's basically 1/27 or minus 0.03704 to 4 digits times v3 now, because I'm basically using this to substitute in to get rid of the v2. And that's equal to 0. And then the second equation, if you follow this dashed line down here, we still have the negative 0.111 v1. And then, again, I want to substitute for v2, so I'll have just v3 bar divided by 3. So I'll divide both of these coefficients by 3. And that will give me the 1/27th again, the 0.03704, except now it's positive, minus just dividing, of course, 3/9 by 3 is 1/9, so it's minus j 0.1111 v3. And then we still have this v3 term, and then the v4 term, we're going to add that since v4 has a fixed value of 8, and obviously 1/8 times 8 is just 1, so we have minus 1 here, so we'll add that onto the right-hand side. Okay. Okay, so I'm just looking at that again. So that's 0.125 times v4. Okay, so that really, oh, I'm sorry, I'm misreading that. That's 0.125 times 8. That got a little bit cut off here is why I'm getting confused. That's just 1. Okay, so equivalently, I could have just written 1 there, but there's a parentheses that's cut off on the paper. So that's 0.125 times 8. So that's just 1. So 8 angle 80 plus 1. And we can easily evaluate that on a calculator. And that gives you 8.2328 angle 73.13 degrees. And just to illustrate that on the calculator, if you like, we have a TI-84 plus emulator here. So, and to enter 8 angle 80 degrees, we want to make sure, first of all, that we're in a complex mode. So, and it doesn't really matter what form we get the answer in, but I've chosen to get it in polar form. So we'd always have to go into modes and make sure that you are set to either polar or rectangular form, depending on what you want. And I've also set the angles to degree, because normally we use degrees with Circuit Tutor. So there we could go 8, and then for the angle, basically I'm going to use this variable e that I've predefined to mean little e to the I pi divided by 180. Remember, that's so that we can convert when you raise this to the power 80, that will automatically convert that to radians in the argument of a complex exponential. That's just an easy way to do that on this calculator because it will not accept that in degrees, strangely enough. So we take that and we add 1 and just click enter. And so that's the value that's shown here, is the 8.2328 angle 73.13 degrees. Okay, and then we basically simplify that equation here. So that's just basically redrawing the equation here. And also, we have to combine the two V3 terms. So when we add the 0.125 V3 to the 0.03704, just doing that simple arithmetic gives you 0.1620. And then the imaginary part remains the same because this has no j. Okay, so that basically produces the simplified form of that equation. And now I'm going to take that and basically combine it with this equation. And in order to make those, basically I want to eliminate one of the two variables. Now I could just solve this for, say, V3 bar if I wanted, by adding this term to both sides and dividing by that coefficient. That would be one way of doing it, expressing it in terms of V1 bar, plugging it in here, and then I just have one equation in one unknown, namely the V1 bar, and I would have to just pull out all the coefficients here and combine them, and then divide by those coefficients to get V1 bar. So that'd be one way to do it, and that's fine. Or you could solve for V1 bar if you prefer and plug it in, or you could solve this equation for either variable and plug it in here. So there's many ways to do this. I'm just doing it by multiplying this equation through, as you would do in Gaussian elimination, by this value of this coefficient, the 0.111 plus j 0.125, divided by this coefficient. And when I do that, and I multiply this equation times that, which is what I mean here, that's basically going to cancel this with this, just to give a -1, and then that'll be the negative of this, which added to this clearly will cancel out the V1 terms. And so I won't have any V1 term left, I'll just have a V3 term. So let's do that. And so the V3 then, I'll have first just this negative 0.03704, which multiplies the V3, which I factored out. And then the second term, of course, I have to multiply the entire equation by this constant factor. And so I'll have this original coefficient of V3, which is shown here, multiplied by this numerator, which is shown here, divided by that denominator. And then all of that multiplies V3 bar. And then on the constant term, I have to do the same thing there. So I start out with, well, 0, which doesn't matter. And then I add it to this, multiplied again times this, divided by this. So that's what we have there. It's written on 2 lines. And then I can just basically take this big expression, enter that into the calculator, and divide it by this big expression. And in the interest of time, I'm not going to type all that out for you, but I just did that in one fell swoop, essentially. Made a lengthy expression, but it was fine. And when I just click enter, I got this value. So it'd be 47.68, angle 105.6 degrees. Again, just enter this expression. Take care that, well, here you don't really need parentheses multiplying these two, but you need a parenthesis around this when you enter in the calculator, because otherwise, of course, you would just be multiplying this times the first number, not times both numbers, which you need to do. So always put parentheses around the rectangular form. And then, of course, you have to use parentheses here and around each of these expressions. So it's basically very straightforward to enter that. And then to find the V2 bar, remember that that was equal to V3 bar divided by 3. And 3 just has an angle of 0 because it's a real number. So that just changes the magnitude only, not the phase angle. And so that gives me just the 47.68 divided by 3 works out to 15.89, the same phase angle. And of course, these are units of volts. And then to find the V1 bar, I have to use either one of these two equations that I combined, either this equation or this one. And in this case, let's see, I guess I used this equation. And again, I don't need the multiplier now, so I just took this number and I subtracted off this times V3 bar. So there's that coefficient, and the V3 bar, then I just put in my value that I just computed, so that's in here. And then I divide by the coefficient of the V1 bar, which in this case is minus 0.1111. And again, just a lengthy expression to enter into the calculator using the E variable that I defined there for convenience. Or if you prefer, you can just use the exponential key and then type in the I pi divided by 180 times 73.13. So you can just do that if you prefer. It's just a little bit more typing. Anyway, you enter that whole expression into the calculator, press enter, and you will get 10.56, angle 57.18 degrees. So that basically completes the solution. And so now we'll just enter those values into the Circuit Tutor interface here. And by the way, I could, if I wished, skip the step of actually entering all these numbers and just go straight to enter the sought variable value. And that's possible to always do that. But I'm just going to go back and check the node voltages first. That way, if there's a mistake, it'll be easier for me to catch the mistake, I think. So 10.56, angle 57.18. And then the V2 bar was this value, so that's 15.89. And the angle is 105.6. And then the V3 bar was, let's see, the V3 bar is, I'm sorry, 47.68. Angle 105.6. And then the V4 bar, that was the easy one, that was just 8, angle 0. 8, angle 0, not 80. Okay, and then we'll just check that. And that is correct. And then those numbers have been printed on the screen. And now the last step, so we have our different variables, also printed out Vx, which we didn't actually enter, but it just computed it for us, which is the same as, in this case, as V2 bar. And so now we just need to compute I naught bar using this equation. So again, that would just give us an expression to enter into the calculator. We'd put negative quantity 8, angle 80 degrees, using probably my E variable that I defined. And then you'd add to that, again, of course, make sure you have parentheses around the V3 minus V4, and that would be this value minus just 8, really, you can enter. And then all that parentheses divided by the 8. And when you evaluate that, that will give us 4.529, angle minus 151.8 approximately. And so we'll check that. And that is correct. And then the last step is to enter these values in the time domain. In other words, to do the inverse phasor transform. And in this case, we will need omega, because remember, whatever multiplies time in the argument of the cosine function, and of course cosine is always used for inverse phasor transforms because phasors are based on cosine functions. That's something you just need to remember if you're doing this on paper, but here it's actually just kind of printed there for you. And the coefficient of the t, by all definition, is always omega. So this is not omega, it's f. And so we have to convert this to omega, and you have to remember that omega is 2 pi f, right? Because there's 2 pi radians in a single cycle, and f is the cycle frequency, or it's the number of cycles per second. That's what a hertz means here. And it's 70,000. So basically, that would be 140 pi times 1,000. So we'll just use the calculator to compute that. So 140 times pi, I'm sorry, not alpha, but second pi, times 1,000 for the kilohertz. So that is, I'll call it 439800 is enough. We don't need all those digits. And this does not accept metric prefixes in this text box, so don't try to put kilo or something like that in there. It would give you a format error if you type that. It'll just tell you that that's not accepted. It has to be a numeric value. Okay, and then since we're looking for I naught here, we use this value, so that's 4.529. And then for the phase angle, that's negative 151.8. And again, the phasor magnitude is the magnitude of the cosine, and the phasor angle is the angle. So we check that, and that is correct. And basically now we finished that problem. If you do want a detailed explanation, for example, if you weren't sure about the sought variable equation, or maybe you guessed at it, or you weren't sure how to get these KCL equations, you can request a detailed explanation by just putting yes there. And it'll basically highlight the equations and show you how these are derived. It'll also give you explanations. If you want a detailed explanation of the KCL, explain the dependent sources, the control variable equations, or the constraint equations. Can all be explained in general there, not the specific ones, but just general explanation. And also the sought variable equation down here at the bottom is described in detail how that's determined. So that would conclude this problem.